in this problem, we have an airplane, and it's going to drop a package to some hikers below. Okay, so initially our plane, approximated as a rectangle, is traveling horizontally, so only in the x direction, at 40 meters per second. So its velocity, v sub naught x, is 40 meters per second. And it's flying at a height of 100 meters above the ground. So exactly 100 meters above the ground here. Okay. And so our question is, where does the package strike the ground relative to the point at which it's released? So at this very instant, our airplane drops a package. Okay, that package, since it's sitting on the airplane, is also going to have a forward initial speed of 40 meters per second in the x direction. And so when that package drops, since it already has some initial horizontal velocity, it is going to execute projectile motion as it falls to the ground. And so that projectile motion is going to look something like this. Okay, actually I probably made it a little bit too steep. It would probably be more curved out here. But anyway, and so we want to find this distance here. Where does the package strike the ground relative to the point at which it's released? So we're looking for this distance right here, okay? And so we'll say that right here, x is equal to 0. Over here is what we want to find. That's our final x position for our package, okay? So that's our unknown for this part of the problem. And then before we go on to solve more for this problem, there's also a few more things we can take care of. Now, our package only has an initial velocity in the x direction. It doesn't have an initial velocity in the y direction, just like our plane doesn't have a velocity in the y direction. So v naught y is going to be 0 meters per second, our initial y velocity, okay? And again, I can choose y equals 0, x equals 0, wherever I want. You choose something that makes sense for your problem. So here, I'm going to say that right where my plane is, I'm going to call that y equals 0. So y naught will be 0. And so where our package ends up on the ground, that will be our final y position. And we're going to say that that's negative 100 meters, because if we think about our coordinate system, this is 100 meters below where I set y equals 0. Okay, now we can solve the problem for how far away does our package land in the horizontal direction. All right, so let's see, using our equation sheet, we'll look to see what equations might be useful for us. Now I'm going to start by writing down this equation here. It makes sense. I want to start to look for the final x position. So we've got x is equal to 1/2 a acceleration in the x direction times t squared plus the initial velocity in the x direction times time plus the initial x location. Okay, now I can go ahead and get rid of some of these things. Our place where we say x is equal to 0, right there, we say that our initial x position is 0, okay? Now we have no acceleration in the horizontal direction. We only have acceleration in the vertical direction, because in the horizontal direction we're moving at a constant speed, okay? So for this problem, our acceleration in the x direction is going to be 0. So that term is 0 as well. So then we have that our final x position is equal to just the initial x position times time. So we know that our final x position is going to be our initial velocity in the x direction times time. Okay. So we know that our initial horizontal velocity is 40 meters per second. We don't know the time yet. So we have to do something else to figure out what this time is going to be. Okay. So what could we do? What other equation could we use? Well, let's see. Let's try this same equation here, except in the vertical direction. Let's say y is equal to 1/2 acceleration in the y direction t squared plus v naught y t plus y naught. Okay, so we said that y naught is 0. We said that there's no initial velocity in the vertical direction. That's 0. So we've got that y is equal to 1/2 acceleration in the y direction t squared. I'm trying to solve this equation for time. We know our final y position. We know our acceleration in the vertical direction. That's acceleration due to gravity. Let's solve this equation for t. Okay, so I'm going to get rid of this 1/2 and multiply both sides by 2. So when I do that, I get 2 times 1/2. That just becomes 1. Okay, so we have 2y equals ay t squared. Divide both sides by ay, a sub y. So t squared is equal to 2y over our acceleration in the y direction. Square root both sides to get rid of the squared on the t. So then t is equal to the square root of 2 times our final y position over our acceleration in the y direction. Okay, so we know that this is going to be the square root of 2 times our final y position, we said, was minus 100 meters when the package is going to land on the ground. And then our acceleration in the y direction, vertical direction, is always negative 9.8 meters per second squared. Okay, so to do this, we've got a negative on top and negative on bottom. So a negative divided by a negative gives you a positive, so we're going to be just fine when we take the square root of this. And we find that the time to fall for our package is 4.52 seconds. Okay, so we can plug that in up here for our time to fall. So then we can find our horizontal position at which our box lands, where the package strikes the ground relative to the point at which it was released. So then this position is going to be our initial velocity in the x direction, 40 meters per second, times the time to fall, 4.52 seconds, and then that is equal to 181 meters. Okay, so that's what this is, this distance, 181 meters. Okay, so that was part A. Part B is to find the horizontal and vertical components of the velocity of the package just before, at the instant, just before it strikes the ground. So right here. So you see, as our package is falling, its velocity vector is like this, right? As it's falling, falling, falling. Okay, that velocity vector has both an x component and a y component. So whenever it gets here to the ground, it's going to have both an x component and a y component. And so that's what it's asking here. What are the horizontal and vertical components of the package just before it hits the ground? So Vx equals question mark, Vy equals question mark. Okay, so we already found a lot of really helpful things to help us solve this problem. We've got a lot of good initial conditions that were already given to us. So to find the final x velocity, let's use this equation. Velocity in the x direction is equal to the acceleration in the x direction times time plus the initial velocity in the x direction. So our acceleration in the horizontal direction, motion in this direction, is 0. Okay, so then this just tells us that the final velocity in the x direction is the same as our initial velocity in the x direction, and that's just going to be 40 meters per second. All right, so that makes sense because we are not accelerating in the horizontal direction as we fall. The only way we could accelerate in the horizontal direction as we fall is if that little package had a motor attached to it that was giving it some additional velocity component, but it's falling under its own accord, and so it's only going to be experiencing an acceleration in the vertical direction. So its velocity in the vertical direction and the y direction will change as it falls. Okay, so let's figure out what it is right before it strikes the ground. So our velocity in the y direction equals AYT plus V0y. Okay, we know we had no initial velocity in the vertical direction, and we know that our acceleration due to gravity is always minus 9.8 meters per second squared. And the time it takes us to fall was 4.52 seconds. So then our velocity in the y direction, just multiply those two numbers, is minus 44.3 meters per second. Negative because we set y equals 0 here. It's negative because we're falling in the negative direction.